Starting the recording now. This will be a review session. Ask me anything you want. I would suggest asking questions from old homework assignments, midterms, and so forth.
Well, nobody's going right now. Dr. Small.
Yeah.
Can I ask a more general question, like a more open-ended one?
Okay.
From each midterm section and the post-midterm 3 material, what would be the most important topic from each one of those?
What do I want to say about that? So I'm going to list more topics than there are questions, because part of the point of giving a test is to get you to review. But you should know how to handle complex numbers. You should know how to do Taylor series from the first midterm, complex numbers and Taylor series. You should know how to find the eigenvalues and eigenvectors of a matrix. You should know how to do vector calculus. You should know Fourier series and Fourier transforms. And you should be comfortable breaking a function down into Legendre polynomials. I would say that Legendre polynomials are more important than Bessel functions. They show up more frequently than Bessel functions. And they're things that you don't need to look up as many details of. Bessel functions are just kind of these things that are out there, whereas Legendre polynomials are polynomials. You can write them down in a finite form. They're not like a Bessel function that you have to represent in various abstract ways. So Legendre polynomials and possibly spherical harmonics. And I'll give you a spherical harmonic or a Legendre polynomial if you need it. I'm not going to expect you to have those coefficients memorized. I'll tell you that this spherical harmonic is, I don't know, square root of 3/4 pi times sine theta sine phi or whatever it may be. But Legendre polynomials, anything involving Fourier series and Fourier transforms, vector calculus, eigenvectors, and Taylor series.
Thank you, Dr. Small.
Mm-hmm.
Can we go over number 3 on the very, I think it was the first midterm?
Okay, let me pull that up. Okay, so the Taylor expansion for this function, we have v is equal to q over 4 pi times 1 over square root of r squared plus z plus d over 2 squared minus 1 over square root of r squared plus z minus d over 2 squared. And I told you to assume that d is much less than z and d is much less than r. So if d is tiny, then d squared is going to be tinier still. So we're going to want to, first of all, get rid of any d squared. So let's just start expanding this out. Okay, well, if d is much tinier than z, That doesn't mean we can just set d equals to 0. There's always some idiot who wants to set d equals 0 and be completely done and just get rid of the variable altogether. All I can say is good luck applying for a job as a university administrator. You'll do well at it. But you have to actually keep the variable in there. But if you've got a couple of terms with the variable, and some of them are way bigger than others, you can get rid of the much smaller ones. D squared over 4 is much less than ZD, so we can get rid of D squared over 4. But if we get rid of D and Z altogether, then we're going to have problems. So we're not going to do that. Then the next thing to recognize is that this is big and this is not as big. Likewise here. So the next thing I would do is I would write I would factor out r squared plus z squared. And we're going to get 1 plus z over square root. Well, no, actually, that won't be, sorry. So writing down square root. Okay, so that's the next step, is to realize that what we ultimately want to do is get this into the form of 1 plus a tiny thing raised to a power. And the square root is a 1/2 power. Now, some people say, I would like to do this the hardest way possible and reinvent the wheel. And then they just take all of those derivatives by hand, which is really tedious. And again, you would have a great career ahead of you as a university administrator, giving workshops on best practices like a discovery that we can revolutionize student learning with take-home assessments, which are assignments that are given to be done at home that assess the course material, and it's a brand new concept. And the rest of us would say, oh, you just invented homework. And you'd be like, no, it's totally different because we did this from scratch with a new name for it. But if you don't want to be a university administrator, then you would look at this and we would say what we've got here is q over 4 pi times 1 over square root r squared plus z squared, something that shows up in both terms. And then I've got 1 plus z over r squared plus z squared d to the negative 1/2. You say, but up above he said a 1/2 power. Yeah, well, it was 1 over a 1/2 power. So that's the negative 1/2 power. All right. So the first thing to do is to always try to take this and express it in terms of a handful of things whose Taylor series we already know. And we should already know, there's basically 5 or 6 Taylor series that you should know. You should know that 1 plus x to the n is 1 plus nx. You should know the Taylor series for e to the x, cosine x, sin x, ln of 1 plus x. If you know those Taylor series, then that gets you a really long way. If you don't know these, then every single time you need to take a Taylor series, you're going to be like the idiot who's giving a workshop where they've just discovered the concept of explaining something or giving an assignment and giving it a new buzzword. Sorry, I was talking to someone about buzzwords earlier in the shows. But the bottom line is, if you don't want to be like an idiot who's constantly trotting out brand new buzzwords for old things, you should really learn those Taylor series. Because then you can start approaching any problem from the viewpoint of, is there a way to break this down into these kinds of Taylor series? Now, once we've done that, then we can look at these two things. We can say, okay, well, here's something with the Taylor series that I know. Here's something with the Taylor series that I know. Now it's just a matter of applying this Taylor series. Q over 4 pi square root of r squared plus z squared times 1 minus 1/2 dz over r squared plus z squared. And I apologize for the fact that that looks a lot like the differential of z instead of this number z times the number d. I apologize for that. But negative 1/2 is the power, or the n in this case, and is zd over r squared plus z squared. And then we subtract off the, and then we've got, let's see, a minus sign here, a minus sign here, and a minus sign there. 3 minus signs is a minus sign. So we get another minus 1/2 d over r squared plus z squared. And we cancel the ones, those go away. We got a minus 1/2 and another minus 1/2. And so what we're finally left with is qz d over 4 pi r squared plus z squared to the 1. And then r squared plus z squared to the 1/2 there. So r squared plus z squared to the 3/2. Any questions?
Can you, I'm a little behind, but can you explicitly tell me why it turns into a power of 3/2?
Yeah, I have the same question.
Because I've got r squared plus z squared in the denominator, or 1. And then I multiply by square root of r squared plus z squared.
Oh, okay.
1 over r squared plus z squared to the 1 times r squared plus z squared to the 1/2. And 1 plus 1/2 is 3/2.
And also, should there be a negative, or was there, because it's negative 1/2 minus negative 1/2, doesn't that equal negative 1? When you add those together and multiply
yes.
through?
Yes, you're right.
Okay.
Anything else?
So this, yeah. So when we took the Taylor series of this v function, if we did try to reinvent the wheel and try to do the derivatives by hand, which is something that I tried to do during the test, when we take that Taylor series of that 1 plus zd over r squared plus z squared, how come we don't have to then take the Taylor series of the whole function itself? Is it enough just by doing it to those parts?
What do you mean we don't take the Taylor series of the whole function itself?
Well, because if I'm remembering how I did the problem correctly during the test at the time, is I didn't really understand what I was doing. So what I ended up doing was just, trying to brute force it and take the derivatives of everything.
Right.
But in the way we're doing it right now, you kind of only take the Taylor series of that, of like what's inside of that parentheses. Like, I guess, I don't know how to formulate the question, but I don't understand.
So you're asking why I only take the Taylor series of the thing I'm circling here
Yeah,
Taylor series of this,
yeah, basically.
because it's a Taylor series in D. Okay, so we're taking derivatives with respect to D. This thing here doesn't depend on D. This thing,
Oh, it's a constant. Okay.
yeah, as far as derivatives with respect to D are concerned, it's a constant. I can have a function of 15 variables, but if I'm only taking a Taylor series of one of them, meaning I'm only expanding as a function of one of those variables, then for my Taylor series, I'm only taking derivatives with respect to that one variable. And for the purpose of the Taylor series, those other 14 variables are constants.
Okay, thank you.
I'll make that concrete. If I've got, say, e to the minus k squared x squared plus y squared, and I have reason to suspect that y is a tiny variable, but x isn't, then I could write that as, well, I can always regardless write that as e to the minus k squared x squared e to the minus k squared y squared. And then I could take a Taylor series of this. And there are two ways to take the Taylor series of that. One is the hard way, to reinvent the wheels so that I can go on to give a workshop where I present known things with new names. The other way is to just say, okay, well, this is e to the u, where u is minus k squared y squared. So that's going to be 1 plus u plus u squared over 2, etc. Depends on how many places I want to take it to. So I'm going to get 1 minus k squared y squared plus k to the fourth y to the fourth over 2, etc. And then the whole function would be e to the minus k squared x squared times 1 minus k squared y squared plus k to the fourth y to the fourth over 2, etc. That's if I only wanted to expand it as a function of y. Now, if someone came along and said, let's also expand it as a function of x, then I have to expand it as a function of x. And there are two ways to do that. One is the brute force workshop presenter way, and the other is to just recognize that I already know the Taylor series for an exponential. And I wouldn't even have to factor it like this. I could just say, all right, this is e to the minus k squared x squared plus y squared, which is 1 minus k squared x squared plus y squared over 2. Sorry, there's no 1/2 there. My bad. Plus k to the fourth x squared plus y squared squared over 2, etc. That's if I'm treating both x and y as tiny enough that we can do the Taylor series. Are there questions on that one before we move on?
Yeah, this question is kind of like to summarize the surrounding, I guess, idea of doing these problems. So for us, it's more important to be able to put functions in terms of Taylor series than we already know than it is to just brute force it, correct?
Yes, because that's how we do 90% of all the Taylor series in physics. Now, there are times when we have to do a Taylor series by brute force, but most of the time we try to use one of these. Just like an experimental physicist usually buys a multimeter rather than making one from scratch.
Okay, thank you.
Other questions?
Professor, I have a question. Could we look at the last problem set and question 5 regarding the drums?
Sure. So, problem set 14, number 5. You were given that psi, the displacement from equilibrium, is Jm of Kr cosine of 2 phi sine of omega t. And we want to know what is omega. And we're told that this is a drum of radius r. And it has to be 0 at the edge. Okay, so we need to find a solution to the wave equation that looks like this and is 0 at the edge. Well, nobody wrote down exactly what the symbol m is, but we're given this information, which tells me that what we've got is J2 of Kr times e to the 2I phi plus e to the minus 2I phi, whole thing over 2. And then if you really want to be picky about it, e to the I omega t minus e to the minus I omega t over 2I, which means that technically we have a solution with m equals plus or minus 2. All right. But whether m is plus 2 or minus 2, we get J2 in there either way. So we've got the sum of two solutions that both have the same type of Bessel function in there. They're both going to have the same frequency. And so what we've got to do now is figure out what is K. Because omega is CK. And we have to pick the value of K so that J2 of Kr equals 0. So Kr must be what's often called alpha 2,1 or alpha 2,2 or alpha 2,3, etc. Yeah, that looks a little bit too much like a 2 instead of an alpha. But Kr must be one of the zeros of J2. It could be the first 0 of J2. It could be the second 0. It could be the third, etc. And omega must be CK. So that must be C alpha 2n over r, where n is 1, 2, 3, 4, etc. Make sense?
Professor, I was just wondering, how can we deduce what type of J number it is by the cosine? Because I know we could rewrite cosine due to Euler's, and then I know we also often write it as e to the im phi, but how can we determine the J's by that?
Because it's a sum of different solutions, and the index of J is always the absolute value of M. And so here we know we've got solutions with M equals plus or minus 2. In both cases, the absolute value of M is 2. If I had written down cosine of 17 phi, then you would immediately know that m is plus or minus 17. And so the absolute value of m, which is the index of the Bessel function, is 17. That's how you know that.
My question is, how did we get from not knowing what omega is to assuming omega equals CK?
Because that comes from the wave equation. When we wrote down the wave equation in cylindrical coordinates is partial squared psi partial r squared plus 1 over r partial psi partial r minus m squared over r squared psi equals minus omega squared over c squared psi, where this is d squared psi by d phi squared, 1 over r squared, all of that. And this is 1 over c squared, and that should have been a partial squared, not a d squared, my bad. Partial squared psi, partial t squared. All right, so the wave equation in 2D cylindrical coordinates is this. And if I were to move this over to the left side, I could just call this k squared. And so I'm left with partial squared psi by partial r squared plus 1 over r partial psi partial r plus k squared minus m squared over r squared psi. So it just comes from the wave equation. We had an omega squared over c squared multiplying psi. That must be k. And then the way that that goes into the argument of the Bessel function is we could divide everything by k. We would get partial squared psi by partial kr squared plus 1 over kr partial psi partial kr plus 1 minus m squared over kr squared psi equals 0. Does that answer your question?
Yes, thank you.
Other questions?
Yeah, I wanted to go over number 3 in the same problem set, if nobody else has a question.
Okay. So number 3 in that problem set. I'm going to start by using the solution to problem 2. So we're told that the flux vector, the flux per area per unit time, minus 1/2 the real part of partial psi partial t star gradient of psi. Now we're going to be looking at the integrated flux. So we're going to be integrating j dot r hat r d phi, because we're going to be looking at a circle in the plane, a circle of radius r. We're going to be integrating over r d phi. All right, so this little element here is r d phi. So, and the element outward from it is the r hat direction. So we only need the radial component. So we're going to be computing the integral from 0 to 2 pi for the minus 1/2 front, real part of partial psi star partial t, partial psi, partial r, r d phi. What we're told is that psi is equal to am e to the I m phi e to the I should have been e to the minus I omega t. That probably explains a whole bunch of minus signs.
Yeah.
HM1.
I remember studying this question after we turned it in, and I couldn't understand why the minus signs were mixed up in the solution. So that's pretty much what
Okay.
I wanted to go over.
Is that what you wanted to know, or do you want me to go through the rest of it?
If you could go over the rest of it just to make sure I have the right thought process, that would be great.
Okay, so e to the minus I omega t. I was wondering why there were, and yes, the answer to your next question is after I'm done grading this, after I'm done doing this discussion section, I will go through them. And if you want to, each one of you before you sign off can ask me if after class I plan to go through and give back the point, and I can say to each of you individually, yes. So partial psi star partial t would be I omega psi star, which would be I omega am star e to the minus I m phi e to the plus I omega t hm 2 of kr, because when we take the complex conjugate, we flip it from the first kind of Hankel function to the second kind of Hankel function. And then partial psi, partial r is going to be am e to the I m phi e to the minus I omega t partial, I'm going to put the k out here, partial by partial x hm1 of x. All right, so when we multiply all these things together, am star, it's going to just become absolute value of am squared. These two things are going to cancel. These two things are going to cancel to 1. And so we are left with I omega k absolute value of am squared hm2 of x partial hm1 partial x. And in the previous problem, we said that we worked out what that product of functions is. And since we're multiplying by an I, the real part of the product when we bring in the I is the same thing as minus the imaginary part. Okay, so the real part of all of that is equal to minus the imaginary part of omega k am squared hm2 partial hm1 partial x, because the real part of I times something, well, I times the real part becomes imaginary, which has no real part. And I times the imaginary part is minus the imaginary part, which is real. So this finally becomes omega k am squared times ym jm plus 1 minus jm ym plus 1 which becomes 2 over pi kr, which is just a fact that we can look up in a table of Bessel functions. And so we finally get omega absolute value of am squared times 2 over pi r. Then we integrate that from 0 to 2 pi, multiplying by r d phi. And, oh, there was a 1/2 out front as well.
Negative 1/2, correct?
Yeah, which would cancel out the plus in front of that. The minus 1/2 would make this plus the imaginary part. And so that 2 and 2 cancel, the r's cancel, and we're left with a 2 pi from the integral. So we get 2 omega absolute value of am squared. And then on today's follow-up, all that you basically had to recognize is that if I've got psi star, derivative of psi star with respect to t, derivative of psi with respect to r, well, that's going to be the product of two sums. We're going to have a sum from m1 equals minus infinity to infinity of yada, and a sum from m2 equals minus infinity to infinity. So you got a yada yada here, which was a great Seinfeld episode. And when we multiply these two things, we get many, many terms. You get all possible combinations of m1 and m2. We get m1 equals 1 and m2 equals 1 and m1 equals 3 and m2 equals 57 and whatever else. But when we conjugate them, we get the sum over all possible m1, m2 pairs, e to the I times m1 minus m2 phi. And I think the way I wrote it down would probably be minus I, but it's not going to matter. Times yada yada. And when I integrate all of that, well, that integral goes away if m1 is different from m2. So when all the dust settles, we get the sum from m equals minus infinity to infinity of problem 3. That's what we get. Because each of those terms, we get all the things with different m values go away. And so we're just left with terms that involve a single m value. And so we're just left with the sum of problem 3. So all you really had to do on today's follow-up was just show me that that integral goes away unless m1 equals m2, and we're left with the sum of problem 3. Which is something that we saw before with Fourier series. Remember, we would, when we derived Parsifal's theorem, we would multiply two Fourier series, and we're getting all sorts of combinations of frequencies, but the product of sinusoids with different frequencies integrates to 0. It's only when they have the same frequency that you get something non-zero. We saw it with Legendre polynomials, where if we multiplied two functions, we get a whole bunch of cross terms, but it's only when we've got a particular Legendre polynomial multiplied by itself that we get a non-zero integral. Every single time we do something like this, if we multiply sums over orthogonal functions, all of the different functions are orthogonal to each other. And so we only have to worry about the cases where we've got two of the same function multiplied by each other, that we get a non-zero integral. That's the structure of this. That's the structure that you're going to see again and again when you do certain expansions in E&M, when you do expansions in quantum. Any questions?
Yeah, I had a clarification on when we took the derivative of psi with respect to r. I understand we're in cylindrical coordinates, right?
Yep.
And so in our case, like we have r, phi, and then t. RT would be like quote unquote the z-axis, correct?
Why is t the z-axis?
Well, it's not the z-axis, but because I looked up at the gradient in cylindrical coordinates, and it gave us a bunch of stuff. And I
Oh,
know
it gave
that
you something with the derivative with respect to z. Yeah, if it's a 3D problem in cylindrical coordinates, you're going to have a z coordinate. If it's a 2D problem, then derivatives with respect to z are 0.
Oh, okay, right. Okay, cool. And I know that we don't take the derivative with respect to phi because we're only worried about the radial component, correct? So we don't have to really worry about that.
Okay, and by the way, there were questions just came up in the chat. Will I go over something from the follow-up? I'll do that in a moment as soon as I clear up this issue with derivatives with respect to phi. Well, I mean, if I want a gradient, there's two different questions I can ask. If I just want the full gradient, there's absolutely a term that involves a derivative with respect. But we were doing an integral where the outward direction, we're not trying to compute just any old gradient. We're trying to compute the flux through this surface, okay? And the flux through this surface, the vector perpendicular to this surface is in the radial direction, okay? And so I need j dot r hat, which means I only care about the derivative of psi with respect to r. If I wanted the full gradient, yeah, absolutely. I would have to take derivatives with respect to phi and compute the full gradient. But I only wanted j dot r hat. That simplified this.
Okay, cool. And then just last question on this problem.
Yes.
When we took the derivative of psi with respect to r, on the right-hand side, we're taking the derivative of the Hankel function with respect to x, and we just say that x equals kr. That's just a regular substitution, right?
Yes, that's just a U substitution. We're just using the chain rule. And Congress has not repealed the chain rule, so the chain rule still holds. You learned it freshman year, and Congress didn't repeal the chain rule. They probably won't be repealing any rules as long as the two houses of Congress are controlled by different parties. So continue to use freshman calculus rather than worrying that the chain rule was repealed.
Okay, cool. Thank you.
Okay, now the question in the chat was, can you go over the first bullet from question 2 on the follow-up to problem set 14? Sure, let me pull that up. There's also a question, is the yada yada episode also the anti-identite? I don't remember. I just remember the story about the bisque. And people keep saying yada, yada, yada as a way of shortening things. Okay, the first bullet point. Follow up to problem set 14. So I've got 1 over n squared d by dx psi equals minus omega squared over c squared psi. Now this does not look quite like the Sturm-Liouville form that we were dealing with. It was written in the problem as d squared by dx squared, but I'm just writing it out like this to be a little more explicit. because what we're used to is d by dx, p of x, dy dx equals lambda rho of x, y. Well, I can take this thing and I can put it into that form if I say d by dx of 1 times d psi dx equals minus omega squared over c squared. This is our lambda, n squared of x psi. Just multiplying both sides by n squared. So this becomes our rho. P is 1. And then the orthogonality has to be that the integral of psi I star n squared of x psi j star, the subscripts I and j meaning that they correspond to different eigenvalues. Is that what you wanted to know, Madison, or do you have questions about that? Now this is different from the previous one where we had d by dx of 1 over n squared, d psi dx equals minus omega squared over c squared. In that case, this is p, not rho, even though the Greek letter rho looks quite similar to the English letter or Latin letter p. But they are crucially different. So p is 1 over n squared, and then the rho in this is just 1. So there are different orthogonality relationships. And what these correspond to roughly are actually different types of EM waves, different polarizations, transverse magnetic and transverse electric. But you'll deal more with that if you take the wave optics class.
Hey, Dr. Small.
Yeah.
On the homework, did they make C a function of NX? And would that give you different orthogonality relationships or different rows?
If I made what a function of NX?
C. I thought it was like a V NX or something.
Ah, okay. So V is C over N. But C is constant.
Oh. Thank you, Dr. Small.
You're welcome.
Professor, I have a question about this problems. I like the analogy that you said about like, reinventing the wheel and stuff. But when I look at this problem, I can't find a way to I essentially fit it where we could make it look like a Hermitian or a Laguerre or a Bessel. But because I guess with those equations, there's specific p values and rho values. But I don't know any equation that has a is it rho? Yeah, a rho value of n squared.
Well, for this one, things are sufficiently different that you can't just say, oh, well, the solutions must be Laguerre or must be Hermite or must be Chebyshev or must be whichever 19th century mathematician. But you can still at least fit it into the general structure here. So even if you can't fit it into a structure with a name, even if you can't fit it into a case with a name, if you can at least fit it into that structure, then we immediately know that the integral of yi, yj, rho dx is 0 if I is not equal to j, assuming we have suitable endpoints.
Okay, so I guess you could correct me if I'm wrong, but so all we should really care about is put it in the form of a Sturm-Liouville's generalized form, and that form also abides to the Hermite equation form where like
No. Hermitian.
Hermitian. Okay, yeah.
Something that's Hermitian is different. The Hermite equation is one particular equation. It's unfortunate that Hermite got his name on both a particular equation and an entire class of operators.
Oh.
There's a whole class of operators that are Hermitian. Lots and lots and lots of operators are Hermitian.
Okay.
One of those Hermitian operators gives you the Hermite equation.
Oh, okay. Okay. So one of them is a form and one of them is an equation. I guess. Okay. But anyway, so the Sturm Louisville's form, I guess, abides to the nature of Hermitian
It has a Hermitian, it is a
nature.
Hermitian operator.
Okay. Okay. Thank you.
Dr. Small, how would we go about solving for the eigenvalues when we have it in
Sturm-Liouville form?
No, when we get to the orthogonality relationship?
You wouldn't. The orthogonality relationship does not automatically give you the eigenvalues. The orthogonality relationship is just a useful thing for checking your solutions and a useful thing for applying your solutions. So I asked you to find the orthogonality relationship because that gets used for its own sake. It's not necessarily the automatic path to finding the eigenvalues.
Okay, that makes sense. But I guess what you're really hearing is just I'm wanting more substance behind the orthogonality relationship.
Orthogonality.
Yeah, orthogonality.
So why do we care about the orthogonality relationship?
Yep.
Because it enables us to do things like we did in problem 3 or in the other follow-up, where, in the other follow-up problem, we took a completely general solution and we broke it down into, we said this completely general solution is broken down into pieces with different m values. And when we want to calculate a flux, we're multiplying two series. Each of those series has a whole bunch of terms, but most of the terms are orthogonal. Most of the terms in one series are orthogonal to all of the other terms, almost all of the other terms in the other series. And so when we take that product and integrate, we're only left with one pair of things.
Okay.
We're only left with specific pairs of things. And so likewise, if we were to do a physics calculation where we multiplied psi by psi and integrated, depending on which orthogonality relationship is obeyed, that might have a whole bunch of things go to zero, it might not.
Okay.
I have the integral of psi I, psi j dx. It depends whether or not we can use orthogonality to simplify. It depends on whether we satisfy this equation or this equation.
Got it. Okay. And then you just sparked my curiosity about the problem we just finished. We said that these cross terms go to zero because they're orthogonal, but in my head, I thought they went to zero based upon the nature of the complex exponent, right? Where when you expand it, your cosines and sines, or your sines will go to zero, but your cosines will either be 1 or -1. When you subtract those from one another, they go to zero. So is that justifying orthogonality, or is that more of just the behavior of a complex exponent?
The behavior of the complex exponents is why the different exponentials are orthogonal. E to the I m1 phi and e to the I m2 phi are orthogonal because the integral of e to the I m1 minus m2 phi d phi equals 0 if I take that from 0 to 2 pi.
Oh, okay. Got it. Thank you.
We can't take an integral that would otherwise be non-zero and make it 0 simply by uttering the word orthogonal. Otherwise, it would be really easy to take a calculus midterm because you could just chant the word orthogonal and then write down the symbol 0 and hand it to a math professor. And they would be obligated to write 100 on the test because you chanted the word orthogonal while writing the number 0. But it doesn't work that way. Orthogonality means that the integral is 0, and the integral is 0 because it's orthogonal, and the integral being 0 makes it orthogonal. These two facts have to go together, okay? Other questions?
But I thought it was more than that. So you're telling me that is the definition of being orthogonal, right? And so
I'm saying that if something is orthogonal, then it must also be true that the integral goes to 0.
right.
Okay, that integral is 0. If I've got two things whose integrals where you multiply them, maybe multiply by a weight function, integrate and get 0, that means they're orthogonal.
Uh-huh.
Okay,
Yes.
that if they weren't orthogonal, the integral wouldn't be 0.
Right. I don't disagree. I'm just wondering if we were to find components of, let's say, Legendre polynomials, and we're looking to see if one component is orthogonal or perpendicular to another, right? I mean, why can we say that they're perpendicular to one another?
Why can we say that they're perpendicular to one another?
Yes.
So look, there's two ways to establish orthogonality. One is to explicitly do the integral. The other way is to, without actually quite doing the integral, proving that if I followed two different paths to the answer, I would get two different constants multiplied by the integral.
Okay.
Proofs that we did had two different constants multiplying the same integral, and yet we started from the same point, and so we'd have to get the same number either way. If I get the same number, whether I take an integral and multiply it by 2, or take an integral and multiply it by 3, the 2 times the integral can equal 3 times the integral, is if the integral is 0. And so I've just proved that the integral is 0.
Right. Okay.
When
I
I
mean,
prove orthogonality, I prove that the integral is equal to 0.
I accept it 100%. I'm just wondering why we can say things are perpendicular in higher dimensions if we take an inner product of two, I don't know, let's say Legendre polynomials.
Why can we say that? Well, okay, so you're asking why that means that things are perpendicular in higher dimensions.
Yeah, exactly.
On one level, to say that, I mean, on one level, it's not exact. On one level, you could argue that it's not exactly the same as, you know, having 90-degree angles, because we can't really draw these angles in
Right.
many dimensions. But what we can say is that we have this inner product operation which obeys all of the same axioms as an inner product in 3 or a dot product.
Okay. So we're just extending that notion into higher dimensions.
Yeah. I mean, I don't know how to like really draw a diagram in 17 dimensions to prove that the Legendre polynomial of degree 17 is perpendicular to the Legendre polynomial of degree 16. But I know that I've got this operation that obeys all of the same rules as a dot product in 3 dimensions. And so it's a generalization of that. let me just note before I take more practical questions that there is a certain type of physics major who likes to say, look, you know, I'm just like, I'm more creative. I want to like visualize things in like all these dimensions, man. But you don't just get to sit there and toke up and say that, you know, you're just too creative for the system, man. Because when you actually try to do these things have, if you want to actually do this geometry at higher dimensions, you have to actually follow axioms. You have to follow mathematical operations that obey the same rules as a dot product in 3 dimensions. Otherwise, you can't extend the concept of orthogonality to more than 3 dimensions. A long time ago, I had just given a lecture on imaging beyond the diffraction limits, something that until about 15 years ago was, well, I wouldn't say everyone thought it was impossible, but I would say that the introductory and even advanced textbooks summarized it as basically being impossible. And the more advanced textbooks said it's a very difficult thing to do that can only be done in a few special cases. And then 15 years ago, people came up with ways to do this all across the board in biology. And so nowadays we visualize things much smaller than the wavelength of light. And after that, a student who fancied himself, and I'm not identifying him because this was a long time ago, and you could say, well, technically I narrowed it down. Yeah, whatever. I narrowed it down to, you know, a very large percentage of students, came to me and said, that's all very interesting, Dr. Swain. I just been talking about the theory of it, but this guy was an aspiring theorist. And this aspiring theorist who fancied himself a string theorist said, it's great that you're doing this kind of theory, you know, doing things that are tremendously practical and prove that the textbooks from 20 years ago were wrong. But do you do any M theory? And M theory is a special type of string theory. And I was just kind of blown away by the audacity of someone who thought that you're not really doing important theoretical physics if you're not doing string theory. You know, given that I'm working on understanding how much information we can pull out of a beam of light and how we can use that to look inside of a cell. And so I went to a colleague who said, that guy wants to do M theory. He's still struggling with C theory, or let alone B theory or A theory. So what I'm trying to say is that it's all very well and good to try to be creative and see like the bigger ideas. But in order to do things in higher dimensions, everything that we know about geometry in higher dimensions comes from thinking very, very carefully about geometry in 3 dimensions and then extending those ideas quite rigorously. The rigorous application of axioms that were first written in 3 dimensions and then suitably generalized. It's not just about see the bigger picture of things, man. It's really about very stringently following mathematical rules. Anyway, somebody must have another question.
Yes, Dr. Small.
Yeah.
When we're doing these orthogonality relationships, how do we get the limits of integration? I kind of understand one for the Legendre polynomials, but
You get the limits of integration because you keep on, if we do the Sturm-Liouville problem, we got d by dx, p of x, dy I dx, and then we multiply by yj star and integrate from a to b. And that will, on the one hand, from integration by parts, be equal to p of x, yj star, dy I dx, a to b, minus the integral of dyj star dx, p of x, dy I dx. And the fact that you can write as this is tremendously important because this is invariant under a swap of I and J. You can swap I and J and you still get the same form. So it's necessary that you choose your limits of integration so that either y or its derivative or p go to 0 at the limit. Okay, and sometimes you're given a particular form for p, like p equals the square root of 1 minus x squared. Okay, sometimes people set things up that way. They only look at problems of that form. If you have things of that form, or p equals 1 minus x squared, if I've got something where p goes to 0 at a and b, then boom, that's got to be your range of integration. Oftentimes in physics, we go from minus infinity to infinity because we have functions that are stipulated to go to 0 so that the function can be normalized. Like a wave function in quantum mechanics, the integral from minus infinity to infinity of absolute value of psi squared, dx equals 1. Or the integral from minus infinity to infinity, and I should really be doing this in 3 dimensions, but whatever, of e squared plus b squared over 2, if I want to calculate the energy in an EM wave, has to be finite, so that I only have a finite amount of energy stored in that wave. So sometimes the physics of the situation will stipulate that we have to consider things that go to 0 at plus or minus infinity. Sometimes the form of the equation or the form of the p of x in the equation will dictate that this, what we call the boundary term here, is 0 at a and b.
All right, thank you, Professor. I just realized we did a lot of that in class.
No problem. This is a review session. Other questions?
Professor, I have a question.
Go for it.
Sebastian, you're gonna. Oh, okay. I have a question on problem set 13, number 3.
Okay, let me pull that up. Okay, so problem set 13, number 3. We say that v of 1 theta phi is equal to big Q, which is a notation for a quadrupole moment, situation where you got 4 charges, half of them positive, half of them negative, cosine of 2 phi sine squared theta plus p sine theta sine phi. P is a dipole moment minus Q. And the question is, what is V of R theta phi? And so the thing to know is that V of R theta phi, as we discussed in class and is also discussed a little bit in the book chapter, is the sum over L and M of YLM, or I should be writing the M up there, of theta phi, 1 over R to the L plus 1 times CLM. So CLM is the integral of YLM star V of R theta phi times R to the L plus 1 d phi sine theta d theta. So again, it's about taking this series and recognizing if we just take inner products with each of the spherical harmonics, we're going to get the coefficients. And then you could say, well, do I have to take an infinite number of inner products to know that I've covered everything? Well, let's see here. In this case, this is basically y2 2 plus y2 minus 2 over 2, because y22 is e to the 2I phi sine squared theta, and then there's some coefficient with, you know, square root of 1 over 4 pi or something like that in there. So this times some constants. So I know that I've got to take inner products with y22 and y2 minus 2, because if I just look in the book at a table of spherical harmonics, I see that y22 and y2 minus 2 have sine squared theta and e to the 2I phi or e to the minus 2I phi. This is y11 plus y1 minus 1, because y11 is e to the I phi times sine theta, and then there's some constants in there, square roots of 3 over 4 pi and things like that that I can't remember, but I can just take those inner products. And then finally, this thing is proportional to y00, because y00 is just a constant. It's not 1, it's 1 over square root of 4 pi. But it just comes from looking at a table of spherical harmonics and realizing there's only a handful of harmonics present in there. To find the coefficients, I just take the inner product of this function with the appropriate spherical harmonic and then multiply. So it's just like it's just not a Taylor series, excuse me. It's just like a Fourier series or a Bessel series or any of these other series of orthogonal functions. And that's what I wanted you to practice with. Does that answer your question?
Mm-hmm. Thank you.
Mm-hmm.
Does anyone want to ask a question before I ask another?
Yeah, Sebastian, Juan, and Kenneth have gotten a bunch. So has Brendan. Let's let other people try a few, and then I can go back to the, you know, premium subscribers on Patreon. Be sure to click like and subscribe. We will be having merch coming out. No, we won't actually have any merch. That would be.
I will buy out your whole stock if you come out with merch.
That would be like so illegal for me to come out with class merch. Actually, I'm not sure if it would be illegal. It would be tremendously unethical, so we're not going to find out. We're not going to.
I was hoping we'd have some Shakespeare references in like some hoodies or something.
A hoodie by any other name would still be something that you wear. Nobody? Okay, tier 1 subscribers.
Question 3 on midterm 2. It's another Taylor expansion.
All right, let me pull that up. Somebody asked, are we your best class this semester? Well, you guys are my only class, or my favorite class this semester. This semester, I'm basically teaching, this constitutes a half load because of the 7 contact hours a week. And some of my time is spent on other tasks. So you are my only class this semester. So you're my worst, my middle. You guys are my everything this semester.
Stop, Dr. Small. You're making me blush.
Well, best, worst, and middle is everything. Okay, it was question 3 on midterm 2, or question 2 on midterm 2, because question 3 on midterm 2 does not have Taylor series in it.
Let me look at it again. Perturbation theory.
Yeah, all right.
Question 2.
Okay, so we had to find the eigenvalues of 0, epsilon, epsilon, e, which is a kind of matrix that you will probably spend a whole bunch of time on next fall in quantum mechanics. Expand for small epsilon. So we just take the determinant of this matrix minus lambda times the identity. So 0 minus lambda, epsilon, epsilon, e minus lambda. That's going to be minus lambda times e minus lambda minus epsilon squared. And we have to set that equal to 0 and solve for lambda. So we're going to get lambda squared minus e lambda minus epsilon squared. Lambda is e plus or minus the square root of e squared plus 4 epsilon squared all over 2. And then you're supposed to take a Taylor series. And so again, there's 2 ways to do it. We could do it the hardest way possible, taking those derivatives by brute force, and then halfway through announce that we've invented something new and give a workshop on it. Or we could just recognize that we've got the square root of a big thing plus a little thing. And so that becomes e plus or minus e all over 2. And then there's the square root of 1 plus 4 epsilon squared over e squared. And that is e plus or minus e times 1 plus 2 epsilon squared over e squared. Because here we've got 1 plus a tiny thing, 4 epsilon squared over e squared, raised to the power 1/2. And so when all the dust settles, we've got 2e plus epsilon squared over e, or if we subtract, minus epsilon squared over e. Any questions?
So you're not expecting us to move past the third term or second term?
I explicitly said in there to only go out to order epsilon squared.
Okay, got it.
What else?
Well, I don't want to waste the time. Any recommendations for the final, Dr. Small?
Allocate the same amount of time that you took on the midterms. And if you want to make full use of the 8 hours, you are, or is it 9 hours, whatever, of the full day, you're allowed to do that. If you've got another midterm that day, then depending on how you work best, either allocate a block before your other final, a block after your other final, or if it kind of divides your day in half, download this final in the morning, take a look at it, maybe do, depending on how you work best, either do a couple of easy things and get them out of the way, or do a difficult thing and get it out of the way, whichever one you'd rather do before your other test. And then after your other test, take a little bit of a break, and then either wrap up the easy stuff if that's the mode you want to end in, or having done the easy stuff in the morning, then do the hard thing in the afternoon if that's the mode you want to end in. But that's my general strategy recommendation for the test.
For problem set number 13, number 4, it was a particular solution to a wave equation. That one, that took a lot of time to sort through and
Derivative gymnastics, and you're wondering, well, I have derivative gymnastics that long. Probably not derivative gymnastics that long.
yeah. Wait, say it again.
You're asking would I have a question that requires that many hours of derivative gymnastics on the final?
Well, I don't expect anything. I mean, I'm not saying I don't expect anything like it. Definitely there'll be a wave equation on there. But is it going to be that scaled or that intense?
I don't plan to have you go through that long of a
Oh, thank God. Okay. Okay, cool.
What would probably be more useful is problem 5, because this is the type of reasoning that people use not just in, say, undergraduate quantum mechanics, but frankly, even in research. Sometimes the most important thing in research is to prove that certain terms have to be 0 no matter what, and prove that other terms are non-zero, and exactly what non-zero value they have will depend on a whole mess of details. But just proving that some of them have to be 0 is important. So knowing when you can use orthogonality relations and when you can't, like in this one, you can't just say, oh, well, y L1 M1 is proportional to y L2 M2, because that's not the entirety of our integrand. You've also got this z in there. But then you could say, all right, well, when I multiply by z, I'm going to be multiplying by cosine of theta. Anything that has different m values is still going to give me 0 integral. On the other hand, things that have the same m values, but different L values, well, now I need to look at how things depend on theta and figure out, will that integral be 0? And the answer might be yes, it might be no. Other questions? Well, how about this? Rather than sitting here awkwardly, why don't we take a 5-minute break? I want to answer some emails and get a drink of water. And then I'll see if there are more questions after a 5 or 6 minute break.
Okay, cool.
All right, I'm back. I can take a few more questions in the next 20 minutes. Anyone has something to ask?
Can you go over problem set 13, number 4?
Problem set 13, number 4. Sure. So I'd rather not do the entire derivative gymnastics, but what I would say is that we've got psi equals y1 minus 1 of theta phi, then sine kr, k squared r squared minus cosine kr over kr. And then e to the minus I omega t. And we can assume omega equals ck. And the question is, does this satisfy the wave equation? So the wave equation is going to be partial squared psi by partial r squared plus 2 over r partial psi partial r plus some angular derivatives, which I don't have memorized, but we can look up if we need that. And all of that is equal to 1 over c squared partial squared psi by partial t squared. And so the question is, does this satisfy the wave equation? First of all, if we take the second derivative with respect to time, we're going to get minus omega squared over c squared psi, which is minus k squared psi. And the thing about the angular derivatives, the property of the spherical harmonic is that if you take all those derivatives with respect to theta and phi and the particular combinations and dividing by all of the proper sines and cosines and whatnot, you get minus L times L plus 1 over R squared times psi. And then you just have to check and see if we take these derivatives with respect to R, do we get something that when added to that equals that? That's the test. Some people tried to make this too hard by taking the derivatives with respect to theta and phi by hand. You can do that. Other people just took derivatives with respect to theta and phi and said, yep, we have an eigenfunction of those angular derivatives. Well, great, we've got an eigenfunction of those angular derivatives. That's good to know, but that in and of itself does not prove that the entire wave equation is satisfied. You had to take all the derivatives with respect to R, add it to this, and see if it equals this. And the answer is yes, they do. Does that help, or do you want me to go through the entire thing? Because I'll tell you, the lesson of it is not really the entire thing. The lesson of it is that you can skip the angular derivatives by just replacing them with minus L times L plus 1 over R squared, whole thing times psi. That's the real lesson of it.
Yeah, that's fine. Thank you.
Other questions? When I re-upload the midterm 3 solutions, I accidentally replace them with the alternative midterm solutions. Sure, I'll do that right now. All right, and then let's see. Yeah, looks like it's the correct solutions now. If you click on it and you're still seeing the old file, you probably need to clear your browser cache.
Professor, I have a question on the format of the final. I know you can't give it away, but is it similar to the midterms where we have like quick questions, and then after that, I
4
guess.
short questions, 4 long questions.
Okay, thank you.
I'm not looking to take up your entire day since I know a lot of you have other final exams that day. So I'm writing it to be the same length as the final. Sorry, the same length as a midterm. Anything else? Well, keep in mind that I'm going to have another session at noon, and there's no rule that says you can't show up to that one to listen in as well. So if no one else has anything, then I'm going to call this over, and I'll upload both review sessions to YouTube later this afternoon. But I'm going to call this one over for now, and then feel free to show up in 20 minutes if you want to see what the other people have to ask.